Hi, everybody. We're going to delve into some of these neurotransmitters and circuits that are prevalent in schizophrenia because that's really how we treat the disease. So let's dive into this. This is not very long, but um, just a little bit about how dopamine is synthesized. Um, it really comes from tyrosine, which enters these neurons that are dopaminergic via a transporter. And then there's an enzyme that convert the tyrosine actually to dopamine. It is then stored in these VMAT2s, which are synaptic vesicles, and it's there for storage until it is ready to be used. So how do you get rid if you have, like too much of it, or you want to stop the action of dopamine? One way is dopamine transporters or DATs, and these actually remove dopamine from that synapse right there, the synaptic cleft, and returns it to the presynaptic terminal where it came from. So they kind of bring it back in, kind of like a reuptake similar to that. Another thing is we have enzymes that actually destroy the excess dopamine. These are MAOAs, Bs, and another one that actually get rid of the excess. Also, norepinephrine transporters, because of the similarities, can transport dopamine as a substrate as well. Even though, it probably prefers norepinephrine, it will transport dopamine too. Now we have receptors. There are at least five significant receptors, pharmacological subtypes that exist. The main one that we target in terms of antipsychotic drugs is the D2 receptors. There's also some presynaptic autoreceptors that kind of act as gatekeepers that actually regulate that dopamine release. So these are the dopamine pathways I mentioned in the last lecture. And we're going to talk about each of these individually, but I put them all on one slide just for your reference. But they're all important in terms of the action of antipsychotic drugs, of dopamine, and also the side effects. First, we have our mesolimbic dopamine hypothesis of schizophrenia. The mesolimbic pathway kind of originates in the brainstem and it terminates in the limbic system, primarily in the nucleus accumbens. That's where it kind of ends. It is thought that excessive dopamine in these areas is responsible for many of those positive symptoms of psychosis, including the delusions and the hallucinations. And this area is also key for our pleasure, reward, and motivation as well. So those antipsychotics that are used to treat the psychosis, they block D2 and thus reduce those positive symptoms. Um, some medication, such as stimulants, actually increase D2 and thus can worsen psychosis or even mimic psychosis if it's used in excess. So it's believed that overactivity of dopamine is responsible for most of these positive symptoms of psychosis, whether the person has schizophrenia or not. It's thought to, and also hyperactivity in this region also accounts for some of the aggression and hostility that you may see with psychosis. Now, another hypothesis is the cortical dopamine hypothesis. This one arises in the ventral sagittal area in the brainstem. It rises from the brainstem as well, but it terminates in the prefrontal cortex. This area is thought to be responsible for many of the cognitive symptoms and some of the negative symptoms that we see. Um, you will see effects of cognition, executive function, and to some extent emotions. So it is thought that actually a deficiency of dopamine in this area is thought to be responsible for these symptoms. So now we're in a dilemma here. We don't have enough dopamine in the prefrontal cortex and too much in the limbic system. Therefore, giving a medication that increases dopamine availability could improve those cognitive and negative symptoms. However, it might also worsen the positive symptoms that you're seeing. In addition, low dopamine levels in parts of the mesolimbic system could account for the anhedonia, lack of motivation, and other negative symptoms that may be arising from this area. So, this is why you may see patients, particularly those on first generation antipsychotics, often have worsening negative symptoms with treatment. This also explains the high rate of tobacco and drug use in individuals with schizophrenia, as these may actually boost the deficient mesolimbic system, in which one would primarily feel pleasure and reward. Um, Another pathway is the nigrostriatal pathway. Dopamine deficiency in this pathway can cause movement disorders, such as Parkinson's. Parkinson's is treated with medications that boost dopamine. Psychosis is generally treated with medications that block dopamine. So you can end up with the movement disorders related to um, blockade of D2. And we'll talk about those in the next lecture. But so there you have a side effect arising from the treatment, which is very common. Another thing, let's just hang tight. We'll swing back to pathophysiology for just a half a minute. If you remember that dopamine is, always being released, from the hypothalamus, right? Going to the pituitary. In the pituitary, we have leukotrophs, and these release prolactin. Oops, sorry about that, and stimulate the breast milk. However, breast milk is not a hormone, and because the babies drink the breast milk, there's not any present in the bloodstream to be detected and induce that negative feedback system. So just remember that the hypothalamus is always on releasing these hormones unless it's inhibited by something. In this case, um, they are off, and when they're activated, they release hormone dopamine. We're always releasing dopamine, and dopamine actually keeps the leukotrophs turned off. It keeps a woman from producing milk because it keeps them turned off as long as you're releasing dopamine. And the thing that will then turn those leukotrophs on is actually the breast stimulation that occurs. So, one of the side effects of antipsychotics is um, gynecomastia, and you're probably wondering why. Well, once you'll see that these antipsychotics actually are dopamine antagonists. They block the D2 receptors, and so because these receptors are blocked, then they're blocking the dopamine receptors in the pituitary gland. So therefore, the leukotrophs are not getting that inhibition from the dopamine, and this can lead to gynecomastia. Interestingly, so while most even second generation antipsychotics can have that issue, there's a couple of them that actually act very different. And we'll talk about that in detail when we get to the detailed portion next week. There's also a thalamic dopamine pathway. This is still under investigation, but it's thought to affect sleep and arousal. So more to come on that. So when you're talking about treatment, the goal, of course, is to develop some drugs that modulate specific dopamine pathways, but don't do the same thing to all of them because of course that can be one of our problems is blocking the dopamine on one hand helps with some of those positive symptoms but can then worsen negative symptoms and cognitive symptoms in other regions. So we're looking to address both the positive and negative symptoms without significant side effects. So they're still improving second generation antipsychotics. More to come on that. I did want to touch briefly on the role of glutamate in schizophrenia. Remember, glutamate is the brain's master switch. It's a We really think it plays a key role in the pathophysiology of schizophrenia and some of the other disorders. It's an excitatory neurotransmitter in the central nervous system, and having it regulated appropriately is critical um, to good brain function. So there's been a lot of recent research looking into glutamate as a possible player here. Glutamate is synthesized from glutamine in the glial cells, and these do play a role in our metabolism. It's released from neurons and can excite virtually everything in the central nervous system. It interacts with various receptors, including NMDA, AMPA, several others. Glutamate is taken back up into cells by transporters and then recycled for future use. So, okay. So some things that we know glutamate does is that we know it regulates transmitters that release from the brainstem centers. And so remember, a couple of these pathways actually emerge from the brainstem. So we can see how glutamate can play a role here. In the corticostriatal, this area connects the cortex to the striatum. We know that's important for cognitive function. So these are these areas, but we know that glutamate has some of the same or similar pathways um, as does our dopamine. So we think it also might be a player in some of the symptoms of psychosis. There's another hypothesis. There's an NMDA receptors, and they're thinking that the hypofunction um, may produce some of the abnormalities that you see in the neurodevelopment in an individual with schizophrenia. Leads to they've seen some effects on GABA. So, and the reason we think this is true is because NMDA receptor antagonists like ketamine and PCC produce schizophrenia-like symptoms in a healthy individual. So that goes without saying that if that's the case, then is there possibly some hypofunction here or something going awry that may be leading to these symptoms? These drugs, it's interesting, they don't just mimic the positive symptoms of schizophrenia, but also the negative cognitive and affective symptoms as well. Um, what they think are happening is that there's an abnormal glutamate signaling at those receptors, and it's disrupting the control of the dopamine systems. Um, it's leading to the mesolimbic dopamine hyperactivity with the positive symptoms and the mesocortical dopamine hypoactivity, which leads to those negative and cognitive symptoms. There's also genetic and environmental factors in schizophrenia. There's multiple genes implicated. You don't need to know all those, but these genes can affect glutamate synapses formation and NMDA receptor function, which could lead to schizophrenia. We also know that environmental stressors such as trauma, drug use, sleep deprivation, stress, and other things can influence, remember, go back to epigenetics, gene expression, which, maybe you have a gene that gives you this tendency, but it's those stressors that kind of push you over the edges. This can cause normal genes that to maybe activate or silence at inappropriate times due to these environmental factors. Another thing they look at is the synaptic plasticity and schizophrenia. Proper expression of some of these genes leads to, our synapses forming and functioning appropriately. Um, Active NMDA receptors do trigger long-term potentiation, which strengthens the synapses and increases the AMPA receptor. So you're like, oh, what does that mean? Well, what it all comes down to is that there may be some genetic abnormalities that lead to these synapses being weaker, ineffective, and not as many in number, um, and not processing them well. And as this goes forward, this could kind of explain those progressive the progressive nature of schizophrenia from those prodrome symptoms to the chronic symptoms we'll discuss more later in detail. So future directions, in the future, we're really looking at more neuroimaging, developing more precise techniques to look at glutamine function in a living brain, looking at gene editing technologies that might compensate for some of the schizophrenia related genetic abnormalities, really personalizing treatment, individualizing therapy, and really looking at that patient's specific genetic and environmental risk. And then, of course, what we're talking about is developing new pharmaceuticals which target some of the specific aspects of glutamine signaling and NMDA receptor function. So, as we understand more and more, I think you're going to see some new therapies on the horizon for psychosis and schizophrenia. All right. Thank you very much. Have a wonderful week.